Welcome everyone. In this video, I want to go over some more problems from chapter 1. And I put the problems for you here. Please watch the last video. And again, I solved some problems. If you check the last video, you have all the problems from chapter 1, all the other ones solved for you. Now we're gonna do some more. So let's go over number 6, section 1.1, and just read the problem. The goal of this exercise is to show algebraically that U with components U1, U2, and V with components V1, V2 are vectors in R2. Then U and V are parallel to each other if and only if this relation works. Now, part A, the definition of U and V being parallel. So let's go over that definition. Two vectors U, V in Rn are parallel to each other if there exists either a constant A, real number, and or B, another real number, such that we can write U equals to A times V or V equals to B times U. So basically, the vectors are scalar multiples of each other, then the vectors will be parallel. And therefore, that means therefore, zero vector is parallel to all vectors in Rn. Since I can write zero vector equals to A times B, and if B is not zero, then we know A has to be equal to 0. So now part B of the problem, it says we want to prove by using the components. So we want to see if that works. So let's go ahead and do that. So if we say we know that U has the components U1, U2, and V has the components V1, V2. U1, and I put here again for U. So the U1, U2, and V1, V2 are the components of U and V. Now, if we say we assume that U equals to AV, then we can write that as A times V1, V2 by using the components. So we can say U is the components of U now, they can be written as AV1, comma AV2. Now, if we write this relation again and we substitute, so instead of U1, we can use AV1, and I use that here. Instead of U2 here, we can write AV2, and guess what? These are exactly the same thing. If you subtract, you get 0, so that works. We can do the other way around. One way I think is good enough, but even if you say V equals to B times U, the other relation, then we can say V is BU1 and BU2, and if we use this to notate the relation now, U1, V1 minus U2, V1, then we can write that as U1 times BU2. So again, that's BU2 minus U2 times BU1, and these are exactly the same thing. So if you subtract, they cancel and you get 0, so it works. Now, part C, if we want to start with this relation, U1 V2 plus U2 V1 equals to 0, if and only if, well, we know that if you take that to the other side, we want to show these two are equal. So first case, if U1 is not equal to 0, that's what the problem tells you to do. So I can say U equals to AV, and that equals to A times V1, V2, and that's AV1, AV2. And guess what? If we go and substitute, so instead of U1, if I put AV1, and instead of U2, if I put AV2, they are the same, so they cancel each other. If you take one to the other side, you get 0, so it works. The second relation, or if you write V equals to BU, then that's the same thing as BU1, U2. And if we substitute again in the relation, we see that the left side, we have BU1 times U1 equals to BU1 times U2, and still the same, so it works. Now, here the case 2, we're going to say U1 equals to 0. If U1 equals to 0, then U1 can be written as 0, U2. and V1 is V1, V2, and we know that V equals to B times U. B times U, the first component is going to be 0, and the second component, if you multiply, then it's going to be B times V2. So here, again, we want to check to see if U1 V2 minus U2 V1 is 0. So it's going to be U1, so which is 0, times here we have V2, which is VU2 minus U2, then this one is going to be 0. So the answer is 0. So that checks. And if you and we are not parallel, I did this one part of that and it works. And here the problem says write down the contrapositive of the theorem that we proved that. If we write that, we can say if U1 and U2 are not parallel, then A equals to A is not equal to UB, and B is not equal to B. And if you use that in the relation, it's not gonna work. So part D, I kind of did that fast, but that's good enough. So now next problem is section 1.3, number 9. It says show the line L given by this equation. This is the vector equation. So x, y, z equals to, again, 3 minus 4, 7 plus t times 4 minus 3, 6 is completely contained in the plane pi with Cartesian coordinate of that. Now, if you want to know if the line is contained in this plane, what you need to do, you can isolate, find the parametric equations. You know, x is going to be 3 plus 4t, y is going to be negative 4 minus 3t, and z is going to be 7 plus 6t. So these are the parametric equations. You come here and you substitute x by 3 plus 4t, y by negative 4 minus 3t, and z by 7 plus 6t. And if you do that, you want to see if you get the left side will be 9, and guess what? If you simplify, you are going to get negative 9 equals to negative 9. So it is in that plane. So that's how you check. 1.3, number 17, show that the line with vector equation. So we have one line, 2, 1, 5 plus s times 8, 12, negative 4, and the line x, y, z, negative 4, 3, 0 plus t times negative 6, negative 9, 3 are parallel. So, and find Cartesian equation for the plane that contains both lines. So let's start. Line 1 is that, I wrote it again, and line 2 has this equation. Find the parametric equations for both lines. So that's the first one, it's pretty straightforward. X is 2 plus 8s, y is 1 plus 12s, and z is negative 5 minus 4s. You do the same for line 2, and you get these equations. Now, if you want to find the direction vectors, you can isolate t. So for the first one, you can write x minus 2, take 2 to the other side here and divide by 8. So you find isolate s's. So what these are the direction vectors. If two vectors, this direction vector, the direction vectors of two lines are scalar multiple of each other, that means the lines are parallel. And that's what I tried to do. I want to see if that works. So I wrote U1 equals to 8 times U2. So these are the components, the direction vector again for L1, 8, 12, negative 4 equals to 8 times negative 6, negative 9, and 3 right here. And if you can say 8 equals to negative 6a, 12 equals to negative 9a, and negative 4 equals to 3a. And if you isolate a in all three cases, you get negative 4 over 3. So then you can say U1 is negative 4 over 3, U2, or U2 is negative 3 over 4. U1, obviously, they're scalar multiple of each other. Therefore, L1 is parallel to L2. Now, part 2 of the problem, let's double check. it says, and find the Cartesian equation for the plane that contains both of them. Now, there are several ways to do that, but I just picked the way I did it, and I want you to see something. Like if we try to graph it, we have a plane. We want to find the equation of this plane. So what we need to have is the normal vector to that plane. So we have L1 and L2. On L1, we have a point, and again, where the point comes from. So this is the coordinates of a point on L1, and this is the coordinates of a point on L2. So how we can proceed? We have a point on L1 and we have a point on L2. We can find the vector that connects these 2 points by finding the components of that vector, and you just use we subtract them. So I'll call that vector v, which is -4 minus 2 and 3 minus 1 and 0 minus 3. And again, if we go back, what I used, I did that minus that, that minus that, and that minus that. That's going to be the components of the vector that connect these 2 points. Then we can just say, take one of those vectors, and if you cross multiply these 2 vectors, the result will be a vector perpendicular to these 2 vectors. That means, and that's just a normal vector of the plane. And I did do the cross multiplication here. And again, for cross multiplication, there's a video, watch that, please. The component of I, you can hide this, is that times that minus this times this. The component of J, you hide that row, and that row is that times that minus that times that, but it's minus later on when we do the determinants. You're going to see why that sign is minus. And the components of K, you hide this, the K we drew on the column we drew, so it's going to be that times that times that minus that times that. If you do this, then you get this vector, and that's just the components of vector. To find the equation of a line, you need a point and the components of the vector n, or the normal vector. You can pick any of these points you want, and I picked this one, which is easier. So you write the first one, 8 times x plus 4, and that's b, and that's c. 16 times y minus 3 minus 88 times z minus 0. All it's left here, little algebra to simplify. And if you do that, you get -17x plus 4y minus 22z equals to 80. Or you can change all the signs, 17x minus 4y plus 22z equals to -80. I think that's good enough for this video. I will solve some more problems and then upload it on the, record it on the next video. And then we'll start with chapter 2. Thank you for watching and have a great day, everyone.